Okay, so the recording has started. Let me share my screen. Okay, so guys, you can see my screen, right? Can anyone just confirm? Just unmute and you can speak. Okay, okay. So my screen is visible. Fine. Okay. So this is week 4, right? And week 4 will be so week 2 we kind of discussed what is supervised, what is unsupervised, what is reinforcement, and how they are different, but how it is classification, what is regression, those things like basic concepts. So if you have missed those like week 2's lecture, you can just go and visit it in YouTube. Okay, and week 3 what we did, we first discussed week 1, week 2 assignment questions, and then go for a like how we should model a biological neuron, so the perceptron model, right? So we mathematically formalize it and kind of also formulated how, let's say, stacking up multiple neurons would work, and how it kind of translates to the neural network architecture, right? So uh, it's like when multiple neurons are stacked vertically as well as horizontally, how the input is flow, like how the input flows from these like in stack of perceptron layers and produce the output, right? So yeah, so if you can remember, so or otherwise you can also visit that YouTube lecture, right? So yeah, we mathematically formalized neural network as well as the perceptron, and we have seen the activation layers, activation functions, for example, sigmoid, tanh, how they look like, right? Okay. So this week we'll be kind of going with a hands-on approach. Okay. So instead of just learning about the theory, let's just try to go and code them so that we have a better understanding about. So this week's according to the content of the course, it is this the perceptron and support vector machines, right? So we will kind of touch like entirely on the perceptron linear and logistic regression, how they are same. Okay, do some coding examples, and we'll try to touch basics of support vector machine, and then I'll kind of give you a good video guide so that you can go there and learn like in depth what support vector machines are. So one thing you should always know, that support vector machines before neural network come, right? Before neural network came, support vector machines were the kind of the biggest invention of the of its time. Okay, so it's currently it's out of date, or we have more powerful estimators or function approximators. However, the theory behind support vector machine is very, very interesting. So you should always learn these. Okay. So for this week we'll try to focus on all the like perceptron, how we should code it in Python, as well as some of its application, and we'll touch upon a bit on the theory of support vector machine. But maybe you should go and like there's a really good video from MIT, so you can just see it. Next week we can do hands-on examples on support vector machine if time permits. Okay. Okay. So like we'll kind of club week 3 and week 4 assignment clearance together, right? So we'll just keep it for today. Let's go with Perceptron first. Okay. Okay. So let me. And if you have any doubts on the way, you can just interrupt me and ask your questions. Okay. So let me just open up. Okay. So we have our coding environment, right? And this is for week 4. What is a kind of goal today is to copy paste it from here so that we have it in our site. Uh, Okay, and let's just increase the font a bit so that it's visible to you. Okay. Okay. So we'll be so Perceptron. Let's just uh, uh let me connect my graphics pad so it will be easier. Okay, let's make it a markdown row. Now we'll start coding. Okay. So let's just do a kind of me. Where is my wait a minute? I have a connector. I need to get it. Okay. So we need one node. So let's just for once let's just recap the overall structure. Okay. So okay. So we have this type of so biological neurons look like. So I can actually go up. There is a photo picture here. If you can remember that. Okay, so there is this biological neuron. Okay, so what it does from incoming inputs x1, x2, x3, all those things, it actually waits. So the inputs are coming from the axons of other neurons, right? So it kind of receives that input with its dendrons. So each dendron has a associated weight W. Okay, and so what it does, it kind of accumulates all the inputs, weighted inputs based on the dendron weights, and then the cell also have some initial energy B, which is also known as bias for mathematical modeling, and then it gets passed through a function, and the function is represented by the axon, right? So axon performs some function on the cell output, which can be, for example, this spike or step function, right? There are other type of functions we have already seen, this ReLU, softmax, all those things, and it gets output as to the it get outputted to the next dendron of the next neuron, right? So that this is a kind of perceptron, and the generalized mathematical model looks like omega 1, omega 2, omega 3, omega 5, omega 4. These are the dendron weights, yeah, dendron weights, and these are the inputs from the previous neurons, which gets kind of multiplied and summed, as well as the bias gets summed, and then there is some activation function which kind of yeah, which kind of does some non-linear operation on the output Z. So these things are important. Z, okay, Z is the cell output, and then it get applied with an activation function to have Y cap or A activation. Okay. So if it is an intermediate perceptron, if there are no other perceptron, it is mathematically we write it as y cap or prediction. Or when let's say there is another like subsequent neuron, then we write it as A activation. Okay. So this is the entire formulation of perceptron. Okay. So let's just go ahead and write this the simplest perceptron that we can have, right? So the simplest perceptron would be there is a input X. Okay, there is no multiple inputs. There is a input X, and there is a weight omega 1, right? And then it gets through the cell summed. Also bias gets added, right? And then you get, there is no activation. Let's say there is only linear activation. Okay, linear activation is represented like this, linear, and then you get the output as y cap. There is no subsequent neuron. So this is what a simplest neuron look like, a simplest perceptron model look like. Okay, and what it is representing. So what it is representing, what is Z? Um, so this is Z and this is sigma. Now let's just write what is Z first. So Z is x omega plus b, right? Now this is Z, fine. Now sigma of Z, because it's a linear, it is Z only. Sigma of Z is equal to Z, right? Now then y cap is what? Is actually sigma of Z is equal to Z. That means what? X omega plus b, right? Y cap is equal to x omega plus b. So what it is actually representing, it is actually representing a linear, a line basically. Okay, a two-dimensional line. Okay, so why? Because so the represented uh, thing would look like this. Okay, so this is x and this is y cap, right? Now x omega, so omega is the slope, b is the intercept of y, right? So we can compare it to uh, mx plus c, right? Mx plus c equation that we have seen in mathematics, right? Y equal to mx plus c, where c is the y intercept and m is the slope of the line, right? So our equation would look like something like this, where this intercept is b and the slope, what we have, this slope, this is omega, right? Yeah, so a simple perceptron represents a line. So now can anyone just comment that what this, when we have multiple inputs, what that thing represents? You can just unmute and say anything that comes to your mind.
So mix of all the inputs multiplied
Yeah,
by
so my question was, if there are multiple inputs instead of only one, so the general case, right? When I have, let's say, 4 inputs and 1 output. So what this perceptron actually means. So we have seen that if there is only one input, then it represents a plane, represents a line, right?
multiple
Now what?
lines, sir.
Yeah. So this would represent a
Multiple points or multiple lines like W as you have mentioned with the bias.
no. See that
Can we
so
convert it into plane?
yeah, it represents a plane. Why? So we can just go to a two-dimensional representation and understand. See, so if there are two, so actually for four inputs, it represents a 5-dimensional plane. Okay, so let's just see what. So here we have this two-dimensional line, right? 2D line, and see how it is represented. So the input dimension plus 1 is the output dimension. Okay. So if there are 4 inputs, then your output is a 5-dimensional plane. Or if your output is 1, then you have a 2-dimensional thing, which can be a line. So for two inputs, how it looks, right? So 2 inputs, it would look like this. So this is x1, this is x2, and this is y cap. So let's say just write the 3D. So you have this type of a coordinate system, right? So the model can represent a plane like this. So let's say, so it's a linear plane like this. This can be a represented plane. So what are the values? So omega 1, omega 2, and b. So b is same. B is what you expect, right? This one, b. Now, what is omega 1? So if you just slice the plane with respect to x1, right? Then you get a line. So you will get an intersect of the plane and the, let's just use a different color. So if you just slice the plane with a line of line at x at any point, right? So you will get an intersect. That slope, that slope is omega 1. Similarly, if you just intersect the line with respect to x2, so for example, you get an intersect line as this, right? So its slope will be omega 2. Okay. So maybe it is not properly represented in this. Um, let's just use that tool, right? Okay. So what was the tool name? 3D plotter or something. Yeah. So let's just have a 2D line. Okay. So the 5x plus 2 2y plus 3. This is equal to y. Y equal to this. Okay. Oh, sorry, no. Z is equal to this. So this is the plane. This is the plane you have. Okay. Now, what is the omega 1? Omega 1 would be, let's say, x equal to 3. Okay. So you have to have a slice. I is equal. So I have to have a slice at x equal to here. So it will be a upright. It is equal to, so what would be the equation of a plane that is here? It's like standing in x-axis. Okay. So it will be uh, for all values of y, there will be only one x. Okay. Y is equal to z. So not like this. So anyway, you understand the fact, right? So the plane should be one that is standing on x and the one that is standing on y, and the intersect would be this line that is intersecting. Okay. So yeah, just moving on. So the plane should look like which is standing on x and standing on y to have its kind of projections. Okay. Okay. So it's very small. Okay, it got closed somehow. Okay, so for a two-dimensional case, it represents kind of this. So a 2D plane, right? Sorry, a 3D plane. So if there are two inputs, it translates to a 3D plane. Okay. So how we can implement it, for example? So we have to get a data, right? First of all, let's simulate a data that is kind of okay for representing it in a Perceptron model. Okay. So what could be a data? So let's go with 2D first. Okay. So your data could look like this, right? Yeah. So this can be some, let's say 50, 60 data samples you have in your X and true Y. Okay, so you go and collect these data. For example, we can say age, and we can say age and let's say height, right? So our data would not be obviously linear. So nobody grows as they age, right? So it's like so for example, we can limit our age distribution to 24 or 25. Then it's a linear curve, right? So most of the time people grow their height till 25. Okay. So now I have collected my data for multiple people, and it gives me kind of a noisy linear trend. Okay. So now what is our job is to kind of have a regression line or a approximated line which represents the entire data distribution. Okay. So what could be a good data distribution line here? It could be what passes through the middle, right? Or mathematical. So let's just draw it. Yeah, this is the representation line. And what is the criteria? So criteria would be to have it to make this line based in this case, the criteria would be that sum of these errors, these little errors we have, are minimum, right? Same as the linear regression concept. The sum of the errors should be minimum. So your prediction, so this red line represents y cap. Okay. Now your predictions with y, so y minus y cap, that's the error, and error is only uh, modulus, right? So positive, negative, both are errors. So you'll only consider its value, not its sign. So now this error term, this should be minimum, right? This should be close to zero. That is what our objective is. Okay. Now let's have this data first, and then we will try to model it with a perceptron in Python. Okay. So where is our code? So if you have any doubts till now, can ask. So what we are doing, we are generating simulated XY data. Okay. So let's just first we have to, so because we are generating from a from like with simulation, right? So we have to first define what is the actual curve is, and then we'll just add white noise to it. Okay. So let's just create a, let's say X is equal to, import some libraries. Okay, and let's import another library called matplotlib so that we can plot it. Right. I miss a T. Plotly. Now, let's assume that our true data is y is equal to 2x plus 3. Okay. Now let's create it. So we have to create an x axis first. So np dot linear space. This is how you create an x axis. Okay. So it creates all the, like, well, let's say I want from 0 to 25. right? I need to have 100 points. Okay, so it creates 100 points from 0 to 25, including 0, including 25. Okay, now accordingly, I can compute the y2. Y is equal to what? 2x plus 3. Sorry, 2 times 6. Now not like this. 2 times 6 plus 3. Now y is there also. So now what is my true data look like? ld dot plot, not plot, scatter x comma y. Yeah. So this is my true data, how it looks like. Okay. So there are small dots. So if I just sample some of it, it will be more clear. Let's say there is a parameter called mark every or something. Okay. Let's try mark every at let's say 10. Fine. No, mark every not doesn't work here anyway. Let's leave it. Okay. So my true data looks like this. Okay. Now let's just have some white noise added to it. So you will not get some data like this in real world. Okay. So you will only get noisy data. So there will be no perfect x to y relationship like this because we have simulated it from with that equation. That's why it looks like this. Now in real world, you will have this noise component added with x. Okay. So the noise can be generated with np dot random dot random every random uniform, we can say uniform. So it's a uniform noise. Okay. Or you can have a normal noise as well. So you can just go with a normal or a uniform noise. So uniform noise is still kind of something that we don't get in our real world. It's mostly a normal noise. So the normal noise location would be 0. So the noise always have this uh, property location, right? So location means how much, what is the kind of base noise you have. So that much noise will be always there. Okay. So we assume that my base noise is 0 for now. So the noise cancels each other out if I just go and sum everything. Okay. And the scale means how much it vary. Okay. So let's just keep it as 3 or something. 3. We'll see how much it disperses our data. And the size is how much? 100, right? So we have 100 samples for x, y, and then the 100 samples for noise so that they gets added up with each other properly. Just bracket this thing. Yeah. So now see, this is what you will see as a real world data. Okay. So yeah, so this is what a real world data would look like to us. Okay. So now let's see how, let's just mark everything. lt.x label is x, y, right? So yeah, so this is, let's say, our data. Okay. And we already know that the actual true data or what the data from which it is being generated is y equal to 2x plus 3. So if my model reaches 2x plus 3, that is what we want. Okay. Now let's go ahead and build the Perceptron. So maybe so if you are new to Python, see how functions are implemented. So we'll implement everything via functions. Okay. So dev uh, Perceptron, what it takes as input x, right? And it has two parameters. And let's define those parameters up here. Omega is equal, so, and this is a linear model, by the way. So we have only two parameters, one omega, one bias, right? So let's initialized omega to be uh, anything. Let's say 0.1, okay, and bias to be, let's say, 0, okay, or let's say 0. Or let's say to 1. Anything you can initialize it, okay. Now, how the perceptron function would work? These two are global variables, okay. So it is defined outside the function. So we have to mark global. So take global variable w and b and give me output omega times x plus b. So this is a perceptron function. So if you pass x, it will predict a output y cap. Okay. So yeah. So now let's see with this perceptron, whatever like initial omega and b value it has, what is the kind of output we are having. Okay. So y cap. So y pred, we can say y pred is equal to perceptron and then x we can pass x axis, right? The x data we have. Now why we are not currently training the perceptron. So next what we will discuss how to train the perceptron. That is the important part. Okay. So currently we have this data, x and y data, that looks like this. Now we have to model it. So our initial model is with initial parameter omega and b. We have initialized it randomly. Okay. And the model we know that it is omega x plus b, and we are considering it is a linear in I linear perceptron. Okay. So there is no activation function, or you can actually define this. So if you want me to do that, so you can just do activation, or we can do this linear z return z. Now here you pass linear. So yeah, this is how it should exactly look. Okay. Now I can predict all y predictions, and now see how my this looks. Okay. Let me just open this up. Sorry. Y pred is equal to perceptron x, and now let's go ahead and have that y prediction overlaid on our data. Okay, so we can see, okay, what was our prediction, whether it was close to the data or not. Okay, so just have to do plt dot plot and our x and y pred. That is our prediction, right? And just let's say color it as red. Yeah, so this is what our prediction look like. Okay, we can also use this label prediction upgrade, let's say white pred legend. Yeah, now we can see it more clearly. Okay, this was our data, and this is what the perceptron model predicts. Okay, and yeah, so this is where we are at. Okay, now one good thing that comes to my mind now here to discuss was how to measure these performances. Now, by visually seeing that, okay, it is far off from the true points, it is obvious, right? So you can visually tell which model is good and which model is bad. But up to when the error are significant, right? We cannot differentiate between two models that are very close, okay, visually, right? It is very difficult for us. Now, There are metrics that are well established that kind of evaluates these models. Okay, so what are those matrices? So you can think of two, like for example, three or two matrices are there for regression. So this is a regression task. We are trying to kind of regress among these values, right? So my matrix will be mean absolute error, okay, MAE, mean square error, and R2 score. R2 score means how much correlated the input and output is. Okay. Now, where we can get those? Let's just use a library, scikit-learn dot matrix input mean absolute error, mean square error, mean squared error, and R2 score. R2 score. Okay. So what they means differently are, so the mean absolute error you already know, right? So it's taking absolute and then you are getting a mean. So yi minus yi cap modulus, and then you have a mean over all the predictions. Squared, you have a square with that modulus, and R2 score is kind of cross correlation. So y and y cap, how much they are correlated among themselves. So if they are completely correlated, the value would be 1 R2 score. So they completely correlate with each other, and if they let's say decorrelate, right? So the value can be -1. So -1 means it completely opposite. It's completely opposite. So y cap is completely opposite from what y indicates. Okay, then that's where R2 score would be -1. And if they both says the same thing, it is a +1. Okay. And mean absolute or mean square, you already know that's kind of a real value you have, right? So let's just so our y predictions are there, our true y is there, right? So let's just see what like these matrices report. Okay. So so we'll have a function compute performance matrix ICS matrices, and what is the input? Y and y pred. So whatever is the y and whatever we predicted, those are two inputs. Okay. And what it prints out, what it returns basically is a dictionary of mean absolute error to be mean absolute error of y true means y and y pred mean y pred, mean square error, same y comma y pred, and last is R2 score. And these matrices will be different for classification. Okay, so we'll also come to that. R2 score, same, you have y true and y pred, y comma y pred, sorry, pred. Now it returns this entire dictionary of computed matrices. Okay, so compute matrices, I pass my y and y pred. I have these these things. Okay, so R2 score can be minus 2 point this. But let me just read the documentation of R2 score. Okay, so the best possible score is 1, and it can be negative infinity as well. Okay, so yeah, so 0 means they don't correlate with each other at all. Okay, and then as negative as you go, that means you are kind of x and y are opposite. Okay, so it's not 1 and -1, it rather 1 0. 0 means it's not completely not correlated at all, And as you go minus, it's negative correlation. Okay. Okay, just small change. Okay, so now these are our scores. These are our matrices that by which we can compare. Okay, now let's just see if I have my omega 1 and omega 2 values to be little bit different, how my score would change. Okay, and how what will be kind of the resulted picture. So let's just see if my score become the omega becomes 1 and b becomes 2 somehow. Okay, I don't know the true this one. Assume that I don't know. Okay, y equal to 2x plus 3, because you will not know this beforehand. Okay, but let's say somehow we somehow guess that omega is 1 and 2. Okay, now based on that, so by changing the variables here, my whole function would work, because these are two global variables. Okay, so yeah, my prediction would change, scatter would be changed. So let's just name it prediction 2, so that we have both predictions side by side. We'll see what is the impact. Okay, prediction 2, and color it as, let's say, green. Okay, by prediction 2, everything is same. Let's compute the matrices with y prediction 2 as well. Yeah, so see, currently my MAE is 13, so we can see that the mean absolute error is reduced, mean square error it also reduced from 856 to 241, and my R2 score becomes -2 to 0.00 something, right? So what it means is, currently earlier we have negative correlation with the prediction. Now we have somewhat, we are not sure whether they're correlated or not. There are some positive correlation, but not significant. Okay. So yeah, so how it looks in graph? It looks in graph like this. Okay. So earlier our model was here. Now our model is here. Now my question is whether, like, is there any way so that my model can learn this thing on its own? I don't have to. So what we did, we kind of adjusted the weight and bias values, right? Now, is there any way so that we can adjust the weight and bias according to the error I am perceiving? So error we can compute at any point, right? We can just use this metric function and compute the error. Now, so what we did, we kind of see the error, okay, see the graph, and kind of modified the omega and b values somewhere that my error got reduced. So there is a automatic way of doing this, which is called this gradient descent algorithm. Okay, gradient descent algorithm. What does it mean? Let's just understand it first, then we'll implement. And so, guys, if you have any doubts, you can just, yeah, go ahead and ask. Okay, we just have another page, something, page. Okay. See, x is equal to something omega. You have a cell, you have some bias, and then you are kind of doing a y prediction. Okay, there is no kind of there's a linear activation, just will not draw it into here. Okay, so what is your equation? Y cap is equal to omega x plus b, and you have some true data y also. Okay, now our objective is somehow we have to push y cap as close as y. Okay, so what does this mean? So that means if I just take the y here, or keep y there, right? So it's like y cap minus y, that should be close to 0. The differences should be close to 0. That exactly means why y tends to y cap. something like that, right? So our objective is to have this modulus function, modulus error. So this is known as the error, okay? Error to be close to 0. So how we should change, and see, x is independent, right? This one is independent. Sorry, independent, and y is dependent. So to change y, I cannot change x itself. I can only change omega and b, right? To change y cap. So our control parameters are omega and b. And now what we are trying to achieve? We are trying to achieve epsilon to be 0, or the error between y and y cap to be 0. Okay. So our error, this objective functions are represented as j in machine learning. Okay. J is the objective function kind of notation that you see everywhere. So j is a function of what? Parameters omega and b that we can tune. Okay. And what is that function look like? It looks like modulus of y minus y cap. That one we should push to 0. That one we should push to 0 such a way with omega and b, so that this entire j function becomes 0. Okay. Now there is a very good algorithm, gradient ascent. What does it say? So let's say it's a hill climbing algorithm. Okay, just a hill climbing algorithm, and it's very basic, so you can just see and understand it. So let's say I am supposed to climb a hill. Okay, and the hill looks like this, uh, like this. Okay, now I am standing at x equal to here and y equal to here. So I'm standing here. So what is my next move so that I like go up to the hill? So my move can be anywhere, right? My next updated x and y should be here also, here also, here also, anywhere, right? But my objective is to climb up the hill, climb up this like hill, right? So my next update, a possible update could be here. Next possible update could be here, 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 right? So what is the algorithm for that? How should I find out those next points instead of randomly guessing next points, right? So this is our objective, to climb a hill j. Okay, with what? With this parameter x, right? X or something. Let's say we can just mark it as omega also. Omega. Okay, I need to change omega such a way that my next point comes here. Okay. So what would be the approach? So I will take the tangent, okay, gradient of this, and accordingly, so I will update the parameter with its gradient. Okay, so my next update would be omega is equal to omega plus the gradient of j, can represent it as by delta j by delta omega at point omega 0. Okay, so let's say this is omega 0 and this is omega 1. This is omega 0. Okay, so next point you will get is omega 1, somewhere like this. Here, omega 1. So what you do? You basically update the parameter in direction to the gradient of the cost function you are trying to optimize. Okay, and you can always multiply it with some factor LR to kind of scale the value. So instead of jumping far from omega 0 to omega 1, you can also control the maximum step you will take. Okay, so this is the gradient ascent algorithm. So you can kind of realize it with like this. So let's say you are blindfolded, okay, and now you are supposed to climb a hill. Now what you will do? You will, let's say your eyes are closed, okay, and you will try to in your like with your foot, what you will try to understand whether the hill is going up or going down, right? So you will only go that way where you are sensing that my feet is going up or my feet has this upward slope, right? That is the gradient ascent algorithm you are trying to do. So you are following the path where there is where the gradient in the gradient direction. So gradient means where the tangent. Okay, tangent at that point. So if you are standing on top of a hill, the tangent would be always to the upward. Okay, and let's say if you are going down, then your tangent would be, so for example here at this point, right, your tangent would be in this direction. Okay, it will be a negative tangent. So yeah, so you will be going, if you are going down, then you will be taking reverse in the, so you will take in the reverse direction of the gradient. Okay, so you will take in this direction. So yeah, so that's the entire thing. Okay. Okay, so after, so what happens after you reach the top? That's the question. If you like, will you stop or will you keep going? So if you keep going, then it will go downhill, right? Okay, so now if you are going down, see, if you are going down, let's say you are here and your gradient is in this direction, you will take at the backward. So you will take steps like opposite to the direction of gradient, so that you move here, you move here. Whereas if you are going up, you will take steps in the direction of the gradient, so you will go on the top. So now what happens at the top, right? So at the top, this slope is zero, right? Slope is zero. So now the entire this component becomes zero. Now your omega t would become omega t plus 1, and there will be no further change, right? So at here at the top, or let's say at the bottom. So if you are, let's say, going opposite to the direction, or if you are doing gradient descent, so you are reaching at the bottom of the hill. In that case also, so at the bottom you have this plateau where the gradient is zero, gradient, or you can say derivative is zero. So there will be no update to the parameter, right? So you will go, either you will, so if you follow gradient ascent, you will go to the top of the hill and stop. If you follow gradient descent or take steps in the reverse direction of the gradient, you will go to the down of the hill and stop there. Okay, so that's the entire algorithm that we will follow. So what we will do, so just by looking this, so what we are trying to do, we are trying to minimize this function, right? So we'll go with gradient descent, not ascent. So we'll take steps at the opposite direction of the gradient. So my omega parameter will be updated as omega minus. So minus means I'm taking either either the reverse direction of the gradient, right? Delta j by delta omega something, and then there will be some scaling factor that is known as the learning rate, LR. Okay, to scale, so learning rate is a hyperparameter. It should be within 0 to 1. It's what it does, it scales the gradient. Okay, scales how much you update your parameters. Okay, similarly b would be also same. B is equal to b minus delta j by delta b times learning rate. Now these things we know, these things we have it in our global parameter list, right? Now what about these things? How we can compute these two? If we know these two, then it is over, right? We can update our parameter, which minimizes the error. So let's just see. My j is y minus y cap modulus. Okay. Now see, to minimize a function with let's say derivatives, right? The primary requirement is it should be continuous. Okay, so and what this modulus function look like? It looks like this. Yeah, the mod function mod x look like this. Okay, now we cannot directly minimize it because there is a discontinuity at origin, discontinuity at 0. Okay, so what we do instead, so this is a trick, okay, by the way. So we are trying to minimize the modulus of the error, but we cannot minimize it with gradients because it is not derivable at 0. Okay, so what we do instead, oh, we use mod x square, and mod x square is x square. So we basically do minimization of this, square of this. Okay, so our cost function is like what we can minimize directly is y minus y cap square, or basically MAC means square error. Okay, MAC, not mean as, and this was earlier, this was actually mean absolute error. So you can minimize mean square error. Now let's compute delta j by delta omega. So what it 2 into, so we are trying to do chain rule. Okay, so let's just go ahead and do chain rule like step by step. So y is a constant, y is a like y we cannot change, right? It's true data. So y cap is the variable, so we can derivative it with y cap, and y cap we can derivative it with the omega, right? Y is equal to omega x plus b. Yeah, so this is the chain rule. So let's just switch to delta, because we are using delta everywhere. Okay, now delta j by delta y cap, what it looks like 2 into y minus y cap. This is okay, and this part y is equal, so y cap is equal to what, mx, sorry, omega x plus b. So if I derivative with omega, it will be b is 0, so omega would be only x, right? So yeah, so this is the gradient with delta j by delta omega. Okay, similarly delta j by delta b would be 2 y minus y cap. So because I am derivating with b, this whole part will be 0. Okay, and these are partial derivatives, by the way. So if you are getting confused here, why this x only remains, why b is not there, these are partial derivatives. So the rest of the component which doesn't have b or doesn't have omega would be considered as constant. Okay, so this part becomes 0, and the b's gradient would be 1, right? So into 1. So let's just not write x into, it confuses with x. So yeah, into 1. That means 2 into y minus y cap. Yeah. Okay. Now, so what is the update function then? So that's very simple, right? 2 into y minus y cap x, and the second one is 2 into y minus y cap. That's it. Okay, and our update rules are, we are going to go at the, so we are trying to minimize j. So our objective, so our step would be in the reverse direction of the gradient. So these are two gradients, right? Some learning rate parameter times one would be 2 into y minus y cap x, and b is equal to v minus, sorry, p minus learning rate times the same thing, 2 into y minus y cap. Yeah, so this is how you update, the parameters. Okay, now we'll just do this. We'll just do this over all the data points. So this x and y, these are individual data points. Okay, so if I have to, let's say, update the parameters over x samples, so I will do for x comma y, sorry, for x comma y in data, update these things, update these two. Okay, so we'll update the parameters in a loop for all the points. Okay, let's just do it and see what would happen. So gradient descent algorithm, what it look like. So take one epoch. So when you kind of go across all the points, okay, so you traverse across all the points, you exhausted all the points, that is considered as an epoch of learning. So we'll train for an epoch, and these terms are consistent across everything. Okay, so deep learning, reinforcement learning, everything. The epoch means if you are going over one loop over the entire data. Okay, and the entire data I'll be passing here x and y, and my predict function, everything is already defined, right? So x and y, train on x and y, the entire x and y for one epoch. So what would be for xi, yi in, and these are something we are Yeah, we'll zip. So if you know the use case of this zip function, just print it. We'll see xi comma yi. What it does, it basically gives you print for an epoch. Oh, sorry, xn I have to pass. Yeah, so it gives you all the points in a pair. Okay, so you have individual points per loop. So per loop you will have x1, x2, x3, y1, x1, y1, x2, y2 like this. Okay. Now what we are supposed to do, we are supposed to update the global parameters. So let's just define them as global. So we'll take global omega and b. We'll try to predict y cap. So y pred, so yi pred basically. So for ith y, what we are trying to predict. So it is perceptron, perceptron, and we are trying to send x. So we have the prediction too. Now what is the update rule? Update rule is omega is equal to omega minus something learning rate times 2 times y minus, so yi minus yi pred times x. Got it? Now b is equal to b minus learning rate times 2 times yi minus yi pred. Right. Now the learning rate I should define it here. Learning rate I can pass it 0.001 or 0.01 for now. Okay. Something small which regulates the parameter change. Okay. So this is the training step of the. So what we are doing based on the error we are observing, we are kind of taking gradients to optimize the error or minimize the error with respect to b and omega. Okay. And what this training for one epoch does, it loops through the entire data and tries to optimize our parameter omega and b, global parameters omega and b somehow. Okay. Now if I just do it once, it will be very much kind of. Wait, let me just print omega and b first. Omega and b. So these are two values currently we have, right? Now let's train it for one epoch. It's trained. There is no print statement, so you cannot see whether it's looping through all the data points. And now let's see what is omega and b. Wait, wait. Oh, sorry. So see what is the mistake? I have multiplied this with x. It should not be x. Okay, it should be xi. Just make them 1 and 2 again. 1 and 2. Train for one epoch and see. Again, there are two arrays. Why? Okay, so let's see what was the update. Learning rate times 2 times yi minus y pred int xi yi pred. Okay. Oh, see here is the mistake. So I have to pass xi, not the entire array x, right? Now it is fine. So 1 and 2. Yeah. Now I trained for one epoch. Now my values are, see, this minus 7.414 into the power 57 minus 2. So it's almost infinity. Okay. So why it is almost infinity? And let's see what is our computed performance matrix. Okay. With y and y prediction we can pass Perceptron X. So it's very, very big. Why? Okay, so let's just run 100 hundreds underscore range 100 epochs of the same thing. So it's NaN. So somehow the weights are getting exploded. Okay, so it's not. We have to debug it. Let's see. So anyway, so if I do like this, my weights are getting exploded and becoming NaN. So let's print omega and b here. It's NaN. NaN means it's not a number. Okay. Now let's reduce the learning rate. Still becoming NaN. Reduce the learning rate more. So what is currently omega and b? It's minus 67 minus 2. Okay. Reduce it further. Okay, so what is our data look like at this point? X and 3, X and 3, YOLO, X and 3. Yeah, so my model currently looks like this. Okay, it's not learning somehow. Okay, let's try to debug it. Where is our mistake? Y minus y cap times x. So 2 into y minus y cap. Oh, see. See, we found out the mistake. Oh, so it's a very, very silly mistake. See, when I am trying to do this, right? So here, so minus y has to be also derivative. We have to also derivative this minus y. So 2 times y minus y cap and then minus y cap, right? So that means there should be a minus 1 component multiplied with it. There should be another minus y component minus 1 component multiplied with it, because delta j by delta y, this derivative part, right? This minus y should derivative to minus 1. And then we have this x. Similarly here also minus 1. Okay, so my derivative actually looks like.
Can you once again repeat why we are multiplying by minus 1?
Yeah, so like this. See, we have the equation y minus y cap square. So that means what? 2 into y minus y cap into minus 1, right? If I am derivating with minus y, if I am derivating with y cap, this inside component, this part will be also have this derivative. So for example, so what does this mean? J is this. So we assume y minus y cap is another function called p. Now j is what? P square. Now if I want to like derivative with y cap, delta j by delta y cap is equal to what? Delta j by delta p times delta p by delta y cap. Right? So now this part is 2 times y minus y cap. And this part is minus y minus 1. Right? So we missed this minus 1. Just
Yes,
by
I got
doing
it.
Yeah, just by doing a step jump, we missed the -1. Okay, so let's just fix our code. So what will be the fix? I have to have this -1 multiplied here. So multiplied -1 multiplied -1. Okay. So currently what we are actually doing, we are trying to take steps in the direction of the gradient, not in the reverse direction of the gradient. Okay, that's why our cost function kind of increases and weight gets diverged to none. Okay, so now we can see currently our value were like 1 and -2. If I do 10 epochs, my MAE is 12 and my R score becomes 0.75. That is improvement from the last run. And now if I do this, see my YOLO model is kind of a bit closer than the green model, right? Now let's go and run it more times. Okay, let's go and run it not for 100 times, let's run it for 1,000 times. Okay, and see my YOLO model is a bit more closer to the actual data. Okay, let's run it 1,000 times again. So these updates are actually accumulating. So if I am going it running it again, then it's actually updating the latest omega and b values. So total we have run it for 100 and like 100 1100 times. Now again 1000 times, so 200 1000 times we have trained it. My MA is further improved and my R square is, see, 0.75. So it's more closer. It's very correlating with actual data. Yeah, so this is where my model currently stays. If I run it again, it will be more closer, right? And it will saturate. So let's just run it for 1 lakh times. Yeah, and let's see where, and at the end, right, when it reaches the optima, it will stay there. So there is no point of overshooting the data. Okay, so my after 1 lakh iteration, my prediction 3, which is where we are optimizing it, right? It looks like this. So you can see, you can kind of realize the change, right? So it starts around here. Okay, and as we go up, it kind of go and uh, also you can actually have a simulation here. uh, Wait, let me just do a simulation. We have to do it here. Restart it. Matplotlib notebooks were supposed to work. Is it working? No. So there was this magic function, Matplotlib notebook, which allows us to simulate data. Okay, but let's just leave it for now. Okay, we'll see. Uh, okay, let's see. Simulate Matplotlib in notebook. Okay, maybe I have to put it at the top, then it will work. Not inline, it should be notebook. Yeah, now it works. Okay, so So this is what simulation, this see this graph. Now we can update this figure later on. Okay. So let's just go there first. This. Okay, so it update the same graph. Okay, so we'll not run any of the graphs. Okay, so here means we are kind of terminating that graph. So here we are terminating this graph. Fine. Now here we are also terminating this graph. So currently, now we can try to have it kind of this. Okay. So what we are supposed to do, there is the initial omega and b value. We'll train it epoch by epoch and try to plot it. Okay. So it will try to, it will be replacing the same graph again and again. Okay. So cut this. Initial omega b we know. So after each training, we can just have a function def plot plot the print line. And then it plots the prediction line. That's it. With the current parameter. Okay. So we'll pass what we will pass? We will pass x and y. Okay. So after each epoch, we'll do plot the straight line x comma y. Let's see what happens, and then accordingly we can change. So yeah, this one is not defined. The straight line, and after each plot, right? We will after each epoch. Let's say if let's just have this as I, so that we can do some kind of I is equal to, so I modulo 1000. After 1000 epochs, we will do time dot slip 0.1. Okay, let's import time here. So what we'll do, it will slip for 0.1 second after 1000 epochs, so that we can see the change over time. Okay, let's run it. Or equal to. I am not seeing anything. Okay, it is getting plotted so fast. Okay, let's interrupt it. Yeah. So what happened? It gets plotted so fast. We have to clear the see this is the change. Okay, and we have to clear the change as well. Okay. So plt dot close. So let's do the plt dot close at the end. Close. Or plt dot show actually clears the buffer, so not close. Now if I do it, it's still not updating. Okay. So instead of doing this, if I just sleep for all the time. Now can I see it? No, it is not actually flashing the output here. Okay, it is kind of halting it. Maybe I have to do plt.show. Yeah. Is it? It's still not outputting it. Okay. Uh, okay, so maybe I can take help from my earlier code somewhere. Let me see. Wait. Yeah, I can. These are RAR files. See it. So if I just interrupt it, so it is accumulating. So plt dot CLA. Okay, now it is fine, but it's not showing plt dot CLE, and then plt dot draw. So plt dot canvas dot draw. Figure. Oh, yeah, now it is visible. See, is it updating? Yeah, it is updating, I guess. Okay. So we can increase the figure size. Big size to be 7,5. Interpret for now. And let's just start with something very w is equal to, let's say, 0.1, and b to be 1. Okay. Was it running? Okay, and will not sleep for all the updates. Will only try to sleep and clear, sleep and clear for for the 1,000th run. Okay. So now clear, we have to do it immediately after this. So can see this yellow curve. If I zoom in, see this one is going up, right? You can observe it going up, right? It's actually learning with respect to that updates. See, it was started here. It is going up like this. And we can actually also let me utility agent, and then just do p dot tight layout. Restart it. Let's restart. Not plot it. Not plot it. Okay, and let's just also have omega and b values after this. Okay, so omega is equal to something and b is equal to something, and let's get it here. Global omega and b, omega b, and then we use f. Okay, so now the global omega and b values will be also there in the graph. Okay, and let's just round them up to 2 decimal places. So thread 2 is not defined. That's fine, completely fine. Let's just remove thread 2 from here. Yeah, now let's zoom in and see how they are updating. See, omega b and b, they are updating, right? And this is how my graph is improving. So my perceptron is learning this omega and b parameters, and the corresponding prediction curve is improving as the yellow curve. I will wait for some time so that it reaches the actual data. And we can also write the epoch number, right? So it will be, yeah, we can actually write the epoch number here. I, and have it here, /n epoch equal to something, and you pass I here, close it, and we have to also pass I. Now we have passed I, fine. Now run it. Yeah, see there. So as the epochs are going up, we are having this function slowly going close to the actual data. Okay, let's just keep this one running, and we'll go and we'll come back to it and see it later on. Okay, so what we are discussing, where is our graph? It should be running. Okay, so this is what gradient descent is. Okay, and how you should implement it in code. Now, what is the exact solution? Exact solution you have already known, right? You have already know that if you have some data, let's say, and it's already taught in the first week class, I guess. So if you have some data x and y, okay, and it's a linear curve, right? It's a linear data. So you can always do this beta matrix, which is actually omega and b. Omega and b. You can represent beta to be x transpose x inverse x transpose y, right? This is the exact solution, but it only works for linear data. Okay, it doesn't work for
ওর ওষুধ দরকার ও বললো নবনীত কে কিনতে হ্যাঁ হ্যাঁ না ঘর যখন চলে এসেছে নবনীত
okay, so So okay, so this is the exact solution, okay? And what we learned here is the gradient descent solution, which works on any type of data. So it works on classification task as well, but this one doesn't work for classification, okay? Similarly, we will also do a classification. Let's see, and let's go back to our. Okay, so it's more closer now. Is it ended? No, it's still running. So now the updates are very slow, okay, but it is still running. So you have to keep it running for 10,000 epochs. It will take so much time because we have this sleep thing, right? So if we just remove this sleep thing, you can see. Okay, so we remove the sleep, okay, and run it now. Now see it is moving much more faster, right? Okay, we'll come back to it later on. Okay, so what was our okay? So gradient descent we have seen. So we can implement this linear type of model with a perceptron with a gradient descent algorithm. Okay. Similarly, we can do it for a logistic regression task. Okay. So we'll not try to we'll not try to do it like this earlier. Okay. Uh, but let's so mathematically what happens for a logistic regression task. So
Sir, concepts are clear, sir, but what you're doing with the execution of part is also clear. But I think we have to practice more, right, sir? Because you are
yeah,
able to
yeah. So
identify,
see
you have practiced
here
more, you identify
we'll
the errors or you
see
have to do things.
exactly.
Since we
So
are new,
so
I
yeah. So
think
we'll go.
one second, sir. What should
Mm,
we, I think, what should we practice more, sir?
mm,
Where should we learn more? Concepts are as you're teaching, we are able to understand.
mhm.
Since you know the
So
things, you are
yeah.
able
So
to find out the errors or clear the errors, or you know the definitions of the Pythons for like for Matplot or sklearn or so. So you are implementing those things.
yeah.
But
So
since we are
so
new, I am new. I'm
okay.
understanding, but I'm simultaneously doing it on my laptop. But
Okay.
I'm going back, checking your this thing, and then implementing. So
Okay.
what makes us perfect, sir? What should we learn, or where should we learn these things from?
Yeah. So see. So after we have this clear, the concepts clear, right? We will not use this from scratch code. We'll use this. You have this sklearn library allowed in your course, right? So you will
Okay.
be using the sklearn libraries, linear regression, logistic regression, everything. And why this knowing how it works important is because then you know why this learning rate is important, right? Or why or where this. So let's say in linear regression model in sklearn, there is this parameter called learning rate, lambda one, lambda two, and everything, right? So so by doing it from scratch, you are learning how why that lambda one parameter is important or why that learning rate parameter is important and what that exactly do. So okay, evaluating models with matrices are fine, okay, but what they exactly do in terms of modifying the weight and bias parameter, that is important. So so later on, the next part I guess today we'll cover it. Wait, let me. So we'll try to implement it on two real data sets here, right? We'll try to implement it on car price prediction and iris. Okay. Yeah. So I guess in your week's assignments also, right? You are supposed to have some tabular data. You are supposed to run a model and reports its accuracy or RMSE. So those things will be from that your sklearn library. But yeah, so doing it from scratch always help because then you know why this parameter is important or how that weight parameter is updated. Okay. So yeah, so after we have this logistic regression a bit more clearer, we'll move to the sklearn library. So you see that so so I guess I'm going to bit with the theoretical details. Okay, we'll see. Okay, so we see that for linear regression, our optimization task was to have a best fit line of the data, right? But for logistic regression, the classification task look like this. you have some cluster of points here and some cluster of points here, right? Now our task is to have a boundary that separates them two. So this is our learning task, and how they are implemented. So you will be actually, so you can represent this as a 3D thing. Okay, where the prediction y cap is here, and you have those two clusters as here and here. Okay. Now, what is your model is learning? Your model is learning to predict this type of a plane. Oh, sorry. Yeah, this type of plane where your 0.5 probability line, this is your probability. Okay, so 0 to 1. Okay, and this is, let's say, 0.5, right? It lies at the middle. So this is the 0.5 probability line. Okay, so for logistic regression, your activation function is sigmoid. Okay, which help you to kind of build this type of a metafold over your data, where that one class is represented as 0 probability, and the second class, it's a binary classification problem, the second class represents as a like higher probability. So let's say it tends to more than 0.5. Okay, so whenever it predicts a probability in this range, it tries to classify it as class 1. When it predicts the probability in this range, it tries to predict it as 0. So this is what logistic regression does. Okay, now let's go back to our code and see if it has optimized further. Yeah, so now we can see it is currently perfectly aligned with the data. Okay, so now let's go with doing some real data set experiments. So instead of simulated data, let's just stop it. Instead of simulated data, let's go with a more, yeah, remove it. Okay, so we'll try to practice with respect to two data sets. One is car price prediction and IDs. So performance metrics for the classification task, you can see why you cannot move it. I can find. So this entire thing was for regression, right? Similarly, we cannot, we have to import these also. Yeah. Now this is for regression. Restart, clear all output. With my laptop is a bit slow at this point. Okay. Okay. Now for regression, these matrices are fine. Okay. But for classification, the matrices are different. It is uh, precision. Sorry. Precision, recall, accuracy, and F1 score. Okay, and also you can have this classification matrix, classification report, okay, and confusion matrix as your can just have this imported like this, and confusion matrix. All these things you can use as the kind of evaluating a classification solution. Okay, so this is an same thing. You can just paste it here. Recall for accuracy. Also, you can have F1 score, classification report, and confusion matrix. So F1 score, classification report, and confusion matrix. So we'll see what these matrices actually mean. So that is important. So sometimes what happened, you are given a confusion matrix and you are supposed to compute precision recall F1 score. Okay, so these type of things can come in your class, in your exam. Okay, compute precision matrix on classification. Yeah. So we have two use cases. One is this car price and the iris flower. Flower identification. Now let's download these two data sets first. Okay. Yeah, test.csv, train.csv. You have two CSV files. Download. Let's use Google. We have email week 4. And also, so both of them are downloaded. Yeah. And also you can go and download IDs. So car price, you can understand it is just how much your car would cost if you have these much specifications. Okay, if you are selling it. And iris is actually you are trying to predict what type of a flower it is based on the sepal and petal length and width. Okay, so there are four parameters: sepal length, petal length, and sepal width, petal width. Okay, and based on that, we can classify the flower into I guess three categories: Setosa, Versicolor, and Virginica. Okay, so these three flowers we can differentiate. You can just download this data. Raw. Yeah. Or you can just do copy and create it according here. Week 4 in your text file. Iris.csv and paste it here. Save. Okay, I have to also unzip it here. Email the week 4 train.zip. Here the CSV. Okay, now let's try to do these two problems for Scarface. So try to read the data with pandas. Week 4 train.csv, and that's our train here. Now let's see what train here means. So it has some ID, some price, and these things, right? So Levy, I don't know what it is. Manufacturer, model, and then part product year, category, all those things, right? Okay, airbags, how many airbags you have, all those things. So let's just try to first identify some features that we will be working with. So manufacturer, model, these things may be important, but there are so many models. Okay, we should just remove them. So part product year, category, leather interior. Yeah, leather interior you can take. Fuel type, engine value, mileage, cylinders, gearbox type, driver wheel, doors, wheel, color, airbags. These are the features that we will take. So these are the X values that we will take as input. Then mark them as features first. Yeah, and then we'll take only the features. Yeah, these are the features, right? Now we should also see there are so we have to now make everything to a numeric value to work with this type of mathematical models, right? So these are kind of uh, your alphanumeric. These are kind of words, right? Automatic, uh, something like this, right? So these are manual. So these are words. So we have to somehow make them numeric. Okay. So how we can make them numeric? So leather, yes or no, right? So we'll see how many unique values are there. Based on that, we'll try to make kind of numerical representation of all the unique values. Okay. If there are string values, for example. So if I am going with this, right, feature leather interior, I'll see how many unique values are there. Yeah, yes and no. So I can easily make a mapping for yes and no, right? So for yes, I will be mapping it with 1, and for no, I will be mapping it with 0. So that is the mapping for leather interior. Okay. So leather interior is equal to this is leather interior map. So you have to create map for every other feature. So let's see. So fuel type, we can do the same. Okay, so there are other things too. There are label encoders and everything, but because we're doing it for the first time, we'll just go with manual labeling everything. Okay, fuel type, FT map. Okay, we'll represent everything by a unique number. So let hybrid be 0, petrol be 1, diesel be 2, CNG be 3, 4, be 5, and hydrogen be 6. Okay. Now, any other Mileage, you can just remove that kimi part, right? You can just trim that kimi, it will be a numeric value. Cylinders, it's already a numeric. Gearbox. So engine volume, right? Engine volume, it is a mixed column. Okay. So there can be this turbo thing as well. Uh, okay, and this okay, so we'll try to write a clever way of handling this. Okay. Cylinders, box type. So gearbox type, we can do a same type of mapping. Automatic, these are 4 values. Fine. Gbox map. Three. Any other value? Gearbox wheels. Um, drive wheels. Okay, drive wheels. Let's just remove drive wheels because I don't think that would impact price too much. Okay. Doors. So this is, I guess, doors 04 May. So when the doors, let's remove that one as well. Doesn't seem to be correlating with price. Wheel. So wheel, we can wheel. It's a left wheel, right hand drive. Okay. Wheel map. One. Any other features? Color. So color, we can color can have a bias with the price. So these are all possible colors. How many colors are there? 16, right? So np dot 16. So this is how you can also do a dictionary. Okay, putting everything in a zip and then doing a dictionary cast. So this is color map. Okay, and any other features that we have? Colored airbags are already numeric. So we can apply all these feature transforms with the feature. So feature just features. Yeah, so we have to first apply it with later interior. And what we have to apply? Dot map. Map means you are mapping a dictionary. Okay. Map. Similarly, we can just go ahead and 1, 2, 3, 4 maps. For every one will be fuel type. We can apply the map and then fuel type engine volume. I guess it's already a mileage cylinder gearbox type. Gearbox type. Gearbox type. And FT map. GB map. Wheel. WH field map. Field map, any other map? So colored map, right? Last one, colored. So after we apply all these features, right? So yeah, so after we apply all these features, so all these transformations, our data look like this. So everything becomes kind of numeric except for these two columns, right? So you can apply some kind of processing on top of them, right? We can see that there, if there is a string in that column, there will be a space at the beginning. That would be the value, right? So you can just do this type of thing. Apply lambda if for every element applies this operation e dot split at the space, take the zeroth index value, so the volume of the engine, and then cast it to float. Okay, now see it produces the actual volume, okay, without any text. So 2.0 turbo is not there anymore, only 2.0 is there. Update that feature. See, now that feature also becomes float. Now here also similar thing we can do, split at space and then take the zeroth value. That's the kilometer. Same, just copy paste it here. Mileage. Yeah. So this is the entire kind of pre-processing we have. Okay. So after this entire operation, my feature looks like all the values are currently your numeric. Okay. Now I can apply a model. So this is the prerequisite we have for applying any model. So every value should be somehow like mapped to a numerical value. Okay. So now let's just put everything together. After we have the features, this is the entire processing we have. And this step is known as pre-processing. Okay. Step pre-processing feature. Hidden feature. So after we have the features, we can do pre-processing. Processing features, it will transfer everything to here. Now if I say feature, it is also like it is actually in place update. So if I don't return it, that also fine. Now I cannot do 2 times change because 1 time. So to do this, I have to do feature.copy to not make it in like in place. Okay. Or let's just make it in place. Let's just keep it as it is. Okay, pre-processing is done. Now I can model it. So what I can do, so what is the target? Target is TF train price, right? And this is my target price values. Yeah, so this is my Y. Okay, and features are my X. So feature, how I can take the value. The feature X is equal to feature dot values. Yeah, now you can see X is a array, X is a matrix of all the features, and Y is the corresponding, sorry, Y is the corresponding values or prices of the car, right? Now I can easily use scikit-learn from scikit-learn dot linear model import linear regression, right? And use that model is equal to linear regression. Here, see, there are a lot of parameters, right? So we'll see what those parameters means. So if it intercept true means you will consider the bias too. Okay, otherwise it will only consider the weights. There will be no bias component to it. X copy ensures positive. That's not important. So we model now model dot fit. we fit with x and y, right? So x comma y. And now we have the model fit. So everything that we do earlier, right? That entire fitting process here, that gradient descent step and everything. Maybe it is using an exact solution, that x transpose x inverse x transpose y. Okay, because that is faster. Uh, if the x and y matrices are not too big, obviously. Uh, Now I can evaluate it, right, with respect to the training set. So y pred is equal to model dot predict on x. Now I am predicting on x. Now I have the true data as well as the y predicted data, right? Now what I can do, I can measure their scores. So compute performance metrics on y and y pred. Yeah, so these are my scores. So my mean absolute error is this, means square error is this. So there is too much error, right? There is so much error. So we can actually predict both of them simultaneously. See PLP dot plot and y. So if I just plot y, so there is this very high value, right? So we should actually remove it. So whenever we are okay, let me. So there is this very high value. We can just remove that entry. And it is around here. Lt dot x. So y lim, you can limit it from 20% here. It's too much. 30,000. Still, yeah. So this is how your data actually look like. So you can remove this this very high number value. So what you can do, you can just clip it, clip a maximum value to this. Okay, to this value. So what we can do, where is our training data? We can either remove them or we can use np.clip to clip that high values. Okay, so what will be the output? Our model will not perform well for those inputs where the value is skyrocketed. Okay, but it will work better for the other outputs. Okay, so let's fit it again, predict it. Yeah, so my my true values are like this. If I also plot my predicted values, it is like this. So I am far, so the model is far off from the actual data. So let's just see closely x limit, putting x limit to first 100 uh, houses. So this is what the model learns. So the blue one is my actual prices of the households, whereas the model predicts like this. So by this, what we can observe, we can see that the car price data set is not linear. So we cannot do a linear modeling of this data set. Okay. So let's just go and see whether any other nonlinear model would work or not. Okay. So let's do uh, some tree model or something like this. The tree import descended regressor. Okay. Now just replace the model with descended regressor. Prediction. Yeah. Now see my prediction. It's completely overlapped. Right? So you see the idea, right? So it's actually choosing the right model will actually make a difference. Okay. So if I go with, let's plot them side by side, then you will understand. So this is model 1, this is model 2. We'll fit both the models with the same data. Predict two predictions from model 1 and model 2. y is still same. So we'll compute this is for prediction 1. This is for prediction 2. And for prediction 1 was for descent regression, right? So dt. And for prediction 2, it was linear regression. Yeah, so by the matrices itself, we can see that the linear model is very, very much bad, right? Here you can see the regression, the descent regression model is far, far better. 0.98 is the R2 score. So now if I just plot them side by side, 1, 2, it's keep it to 10,000 just to fairly compare everything. And alpha, so prediction alpha is equal to 0.5 and line width is equal to 3, let's say. And this is color is equal to blue. Label is equal to y true. Here label is dt prediction. Here color is red. Let's say here color is green. And the label is linear regression prediction. Yeah. So this is how it looks. So see, my linear regression prediction is nowhere nowhere close to uh, my actual data. So if I just remove the line width to 4, you will see that the blue curve and the green curve, they're actually overlapping. So my descent tree prediction is actually very close to what my true data is, whereas the linear regression model doesn't perform well. So yeah, so and from the performance matrix also you can observe that same thing. So yeah, this is how you implement linear regression with scikit-learn. Now the testing was a bit wrong. So what we used to do is not train it on the test set. It's not train it on the train set. Instead, test it on the train it on the train set and test it on the test set. That would be giving us a good estimate of how it will perform well in real life. Okay, so try to read the test set now. Week 4 test.csv. Okay, now we'll do the same thing. So we'll extract out the features. Test. We do pre-processing on the features. Right. And then yeah, our text X and test Y would be this. So feature is name test. Is it okay? Feature. Yeah. Okay. Now let's test it on these two things. First, we'll try to predict X test to predictions test. Here it will be Y test. What it is saying, input value of NaN. So let's see where the NaN comes. I create one. Okay, so maybe the test features have some NaN values. So what we will do, drop now. So it will drop any NaN values you have. Still also you are getting the same. Oh, Okay, some feature is dropped, completely dropped because of this NaN. So replace NaN with 0. Yeah, so this is our test set predictions. Okay, y test. So it's really bad as far as I can see. Okay, so to score is 0. Did you do pre-processing? Yes. Okay. So there are a lot of missing values in test set. That's why it's not working properly. Okay. So we'll try to see the output. It's predicting test. Yeah. So see the y true is very less. So df test. What is the price? Yeah. See the price values are 0. So that's the kind of your what you will say that there is no data for the price. Okay, and if I just not replace NaN with this okay, maybe it is because we downloaded, yeah, it's NaN, so we have to fill this data and then we can find it in, I guess, where we downloaded it from, right? So we cannot test it with the test data, we can just predict it. For testing we have to have the values here. Okay, but anyway, my predictions for the test state looks like this for both of the decision tree and the linear regression model. Okay, for let's just quickly go over the same with the logistic regression for the classification task, right? So IDs same, we'll just test it for only one model, say logistic regression. IDs and the read data frame week 4 we have iris.csv, and now yeah, so 1 2 3, and this is the target, right? Shwetosa, Virginica, and versicolor, three types. So for classification task, the kind of encoding we will be doing is a little bit different. Okay, so for the test, for the target species, right, we'll try to apply this pd.toDummies function to dummies. So get dummies function, sorry, get dummies. Get dummies and you get the data. Okay, it will kind of give you this type of a one-hot encoding. So when there is Satosa, it will be one versicolor. For that versicolor column only, there will be one for those instances, and Virginica for only the instances where there is this species, it will be one. Okay, so this is your target. Fine, and just cast it to values, and X is everything other than this. So iris dot columns, you can just, or you can just do iris dot crop species columns species. So now you have only the features. So this is your X. Okay, and there is no train set test set. So we have to define the train and test set. And to do that, you can use scikit-learn dot model selection import train test split. Okay, so train test split it takes input as, so you can just go down and see the documentation. There is this example of a trade test split. You can just copy this, have all the parameters there. Yeah. So your X and Y is here. General test size is 0.3, random state is 42. So after running this, I have all the X, Y, X train, Y train, X test, Y test values. Okay. And they're all numeric. So now I can go and model it with import logistic regression, logistic regression. Okay. Now model. So logistic regression is basically a classification model. Okay. So yeah, so these are other parameters like, see, your penalty L2, that means it will be doing this reach type of regression penalty. C1, these are there, so these are not that much important. So multi-class auto means it will either do a binary classification or a multi-class classification based on the input of Y. So here it is a multi-class because there are three inputs, possible outputs. So model, now do model dot fit, and we will fit on the training data only. Okay. So what does it say? Y should be an 1D array instead of say this. Okay. Password and okay. So multinomial, multi-class parameters regression must be string, not a auto. Multinomial, yes, it should be a multinomial. Still, okay. Okay, so I think we don't have to do this. It does it automatically. Okay. It's so get dummies, we don't have to do it, and do it automatically. Let's see. Yeah. So the beauty of these libraries is it does the most heavy lifting part on its own. So you don't have to go and manually get all the things corrected. So why is still this? Okay, still it can manage training the model with it. Okay, so it kind of internally get the dummies and train it. Okay. So let's just make this multi-class thing as auto itself. No, not an issue. Now just test predict by bread train X train and compute matrix on classification I sorry I train by bread train. Okay, so what does it say? There are multiple classes, and by default it's a binary thing. Okay, so for multiple classes we have to go with weighted. The average is equal to weighted for all the matrices. Not all the matrices, few of them. Just copy it. Go to that function we defined earlier. Here, right? Now here we have to pass that thing. So all these things should be like this. Here also maybe I have to give. No. Okay. You can got an unexpected argument average for what? For accuracy. So accuracy should not be average, right? Yeah, so now your precision is 0.96. Recall accuracy is 0.96. F1 score is this, and classification report, you can just go ahead and print it. So met is equal to this met classification report print. So here what it says the precision recall per each of the instances that you have seen. Okay, so it kind of summarizes the entire classification performance. Now this is the training performance, right? Now go with the testing. Just replace everything with test. Metrics test. Train test. Oh, sorry, and we can just print the classification report because it summarizes everything. Yeah. So for the testing instances, we are kind of perfectly predicting everything. And how we can check it? We can check it from the confusion matrix. So confusion matrix, what it gives? Confusion matrix, it gives how many times one class is getting confused with another, right? So the training confusion matrix looks like this, right? So that means in some cases this Virginica is kind of mixed with versicolor, and this versicolor is mixed with Virginica 3 times. Okay, but in testing case, you can see everything is getting we only have non-zero values at the at this at this corner. So you can say that everything is perfectly classified at the testing time. Okay, whereas in the training time, there are some instances which are out of which are not predicted correctly. Okay, so yeah, so this is how you evaluate your classification uh, kind of problems. Okay, and I guess some of your assignment questions have this testing size and random state not mentioned, right? So just go with default values. So the default value is 0.3 and random state as 42. Okay. Or one thing you can do, you can run your code multiple times, get an average of your accuracy. That would be also same. Okay, any questions till now?
Yes, excuse me, sir. Actually, the problem given in the assignment,
Yes.
and I've solved it on Google Colab. The code I have written it with the help of course, taking some help with ChatGPT.
Yeah.
And as you mentioned, I have taken that test size 0.3 random 42, but I am getting different values, and they are not there in the options of the assignment.
See, random state and test size, that what it actually ensures is your data. For multiple runs, your data gets splitted at the same ratio as well as the same order. So you get it, right? So if you set random state and test size as 0.3 and 4.2, no matter how many times you run the code, you will get the same results.
So we have to mention that the same in the code, na, in our code.
Yeah. So you just mentioned it before splitting. So here at the split.
Yeah, before splitting, I have did that. And in the assignment question, they have given different 3 different values for C, and we have calculated the best accuracy for which the given C value. With the help of for loop, I have generated that. Calculate the accuracy for different values of C.
Got it. So the thing is, if you are so how you have written it? You have split the data set before the for loop, right?
Yes. Split the data set before the for loop and define C. Then, can I share my code?
Yeah, you can. I guess you can share your code in the chat. You can share your code in the chat.
Okay, code in the chat. Okay, right.
So the best thing would be if they mention what should be the random state and everything, right? Yeah. So see, if it is very hard to get those options in your results, you can just let's just share the code. Let's see whether there is
Just
something we can change. HG. HG, I can see. Okay. I cannot unmute you. Wait.
And see, there are two questions like that, and even for L1 and L2 regression, they have asked which one is better, and that option is not coming in the multiple MCQs there.
Yeah, you can just hear your code. I will see what like how, which order you have set the these things, and let me also see the code also.
I have taken help of ChatGPT also, and then learn the code from there.
That's fine, I guess.
Yeah, okay, just a minute. I'm trying to copy it, but it is not. Chat window. Unable to copy the code on chat.
Okay, I get the data. So train a linear perceptron classifier on modified IDs dataset. We recommend using scikit-learn only first two features for the model. That's fine. And report the base classification activities for L1 and L2 penalty terms.
Yes, that is there. And next question
so
is also two questions.
Let's just try to do it because we have the exact same thing, right? So first two columns means
it is modified iris data. So I have taken that, downloaded that modified iris data. The link is there in the assignment.
Okay, so let me go to the assignment.
Yeah, link is there in the
This is for
assignment.
week 4, right?
Week 4 assignment, yes.
Week.
And the columns are also not labeled in that data, so I have labeled the columns also. And it is mentioned that you have to take only 100 samples for train and 50 samples for test. I have defined that also in the code.
Is it okay? Use the first 100 sample for training data, and the remaining 50 as a test data.
Yes.
Okay. So the test is all. So the train test split is already mentioned.
Yes, has already mentioned. But even then.
Okay. So got it. You would have seen the first test data set. You can round up the accuracy value to do so, not change the data points. Okay. So I guess now the random seed and everything is not required. Let me download it.
And only two features we have to select. So first two features select.
First two features. So week 1, ID
Sepal length and width I've taken. First two features mentioned in the defined.
Let's see. So if I see the exact same problem that you are facing, then you can just reach out to NPTEL saying, okay, we cannot reproduce the same or something that is here, right?
Okay.
So we have downloaded the data. Okay. Let's see.
In Google Colab, we have to download on the same path, and I've given that path also. I can see that data also. I've printed that data, but even.
Week 1 and then ids.csv.
Yes.
So we have like this. Okay.
Yes.
Okay. So now here I can do header is equal to none, which will give me like this, and then I can only choose two columns, right?
Yeah.
So dot ilog.
Yeah, with the help of ilog. Taken two features, 0 and 1. Yes.
0 to 2, and
Zero.
then every value from 0 to 2. Yeah, only two columns, right?
Yes.
So this is the entire X data. You can just values and you can just split everything according to them. So X train, right? X train is
yes, and that is
first 100 values.
First 100, yes.
So 100. And then similarly, we can do x test to be 100 to the rest.
Yes.
And we can have these dot values, right? To make them as sorry, this is test. And similarly,
for
yeah,
test it's 50. Last
yeah,
50. So it will
last
be
50, right? So there are 150, 150 values. So
yeah, there are
till
150.
100 to the rest. Okay.
So it will go from
So similarly, we can have IDs Y, same 150 values. Similarly, I log
I log
0 to
100
100.
and 0 to 50.
This column I should
100 to
not give.
150.
Yeah, so this yeah, so this right.
Right.
And
And for test it will be for Y test it will be 100 to 150.
values dot flatten. So it will kind of flat everything out.
Okay.
So this is Y train.
Y train.
$100 to the end.
Yes.
Okay. Now if I just do the same thing, just remove everything.
The learn train split, yes, that is there. Yes, that is there. Okay.
Registry regression you have to do. Now here for penalty term. So you are supposed to do logistic regression, right? Your linear perceptron classifier, that means logistic regression. Okay. We recommend using scikit-learn for.
Okay, we'll not go for SVM. We have to go for
No.
Okay.
So logistic regression classifier. See here they have clearly mentioned that you have to use a linear perceptron classifier. That means it's a logistic regression model.
Okay, maybe that is the problem, I think.
So let's do this.
They'll put the linear model logistic regression, then you will try.
Yeah.
Okay.
Yeah. Penalty L1 for penalty L1.
Yeah.
And let's say this is model 1 and this is model 2. L2. Let's feed both of the models with the training data. So what does it say? Only L2, non-penalties got sulfur LV supports only L2. Non-penalties got L1 penalty. Okay, so you have to use what? L1 and L2 penalties. Okay, so we'll see. Solver is this, right? So solver does not have L1. Okay, let's see what we can do. Okay, this one. Solver should be that one. Okay, now we have fitted both two models with L1 and L2. Let's try to predict one train. Two train. Two. For one. It's for two. And you can just print their classification report. Let's see. The trading. This is for the training, right? And for the testing, we have to do the same thing again. So let's test
Performance meter.
here. Test. Same thing. We can do metric 1.classification. 2.classification. So here our accuracy is 82 and 68. Is there any option?
No.
82 and 68, right? There is no option.
No option is there, right? That was the problem.
And you are getting also 82 and 68. A similar. You guys are also getting the similar output or what? Now, I guess it is this perceptron scikit-learn linear
0.71, 0.714. Sometimes it is different values I'm getting.
No, so it should not be different because your data split is already defined, right? So
Yes.
it should be only one. So even if I run it again, right? See, my model would not give me different accuracy.
Yeah, actually, I've done different that RF value and checked for different options and whether I'm getting any option related to that MCQs. That's why.
So it's 82 and 68 at my end. 82, 68 is closest to this option. Okay, so let's just see whether there is a perceptron model in it. So maybe we are using a linear model that perceptron. Okay, linear model that perceptron, and then
linear model perceptron के लिए किया तो it is coming to be.
For classification, is it for classification?
Linear model dot perceptron किया था इसका linear model.
Class weight is there. So let's just use this model once.
Linear model dot perceptron. I'm getting the accuracy. The accuracy with perceptron L1 L2 0.7143. It is something.
Yeah,
like
so 0.7143 is there, I guess.
0.743.
And so this
0.7 is there, but for L1 L2 0.71 0.7 it is not there. 0.71 for 0.65.
So I get 0.78, 0.64.
Okay, 0.78. Okay.
Yeah, it's there.
Yeah, that is there. But I will try for a linear relation.
So yeah, so only replace this model with perceptron model. It will be
linear model perceptron. I have done that also. I have did that also.
Second one, training SVM classifier on the modified data set. We recommend use external feature, encourage you to explore the impact of varying different hyperparameters of the model, specifically try different kernels and associated hyperparameters as per the assignment. Train model with the following set of RGF kernel gamma 0.5, 1/6 test classifier, no feature normalization, try C in this and report the best. So this is conclusive, right? So you can just go and train, and the model is SVM classifier, SVC.
Yeah. Okay.
So from
this model will be
from scikit-learn dot SVM import SVC. SVC, this model. Okay, SVC, and here you can keep changing all those parameters and everything. You see, it's already there, so you can just keep changing them, testing it. So I would suggest make the entire testing code as a function and pass the model as the input of that function, so that you just change a parameter, pass the model, get the output as the accuracy.
Okay. No need to use for loop and different values.
Yeah. So you can obviously use a for loop, but put the entire training and testing code in a function and then change loop through the model. So you can also pass the model as the function parameter, right?
Okay.
So yeah, just pass the model as the function parameter with varying parameters, and then just
Right.
take a max of the.
And compare the results of all the three.
Yeah.
I can do that also. Okay. That will be.
So I'll share this code so you can have a kind of reference to it. Okay.
Yes, I will take.
Okay. So I guess that modeling thing was clear, right?
Yes. Nice.
So there is no error, thankfully.
Yeah.
Okay.
Thank you, sir.
Okay. So guys, we'll much over the time, so we'll just stop.
Yeah.
Here, and next week I guess we will start looking into SVM's theory. Okay, SVM theory. So in the slides I have linked this video. So this is a very good video from MIT, and this guy explains the SVM theory very easy, like very easily, and how it was the best classifier of its time. You can understand by looking into the video. Okay, just see it, and later in the next class we can dig deeper on two SVMs. Okay, and also in the next class we will clarify any doubts from week 3 and week 4. So I found it better to club 2 weeks so that we have a significant doubt clearing session for week 3 and week 4 next week. Okay, instead of going like per week every week. Okay. Okay, I'll stop sharing. Thank you guys. So see you in the next week.
Yes,
Bye.
thank you. Thank you.